So this morning we had symmetric key. So this afternoon you will get public key cryptography. We hope that it all works very nicely. It seems so, we're almost there. And so this talk will be given by Krijn Reijnders, who is a postdoc in our group.
All right. Good afternoon, everybody. So my name is Krijn Reijnders. I'm a postdoc here, actually in isogeny-based cryptography, but I'm taking over today for Wouter, who couldn't make it, on public key cryptography. And it's really basically an introduction to public key cryptography. So we're really going to go over quite a few of these basic things, like modular arithmetic again, or what is RSA or Diffie-Hellman, really to get everybody on the same pace for things that you would also need in the rest of the week. I could imagine that you've already seen maybe modular arithmetic once, or you've had like an intro to cryptography course and you've seen RSA and Diffie-Hellman. And if that's the case and you want to be on your laptop, for me, that's fine. The only thing that you need to be aware of is that at some point, we're going to have a magic trick. And then you actually need to pay attention because you're involved in the magic trick. Having said that, so what is actually the goal for me today? The goal for me today is that when you see these sort of cryptographic protocols or you see these descriptions, you'll often see these things like this is when you signed up for the course, the certificate that was used. You see these things like RSA. And here is for WhatsApp. When you're using WhatsApp and you're looking what's inside WhatsApp, you see these things like curve 25519. And my hope for me today is that after about 90 minutes, you actually understand what's going on here and why is that, what does that algorithm mean and why do we need a specific curve? What is even a curve? And so that later on, if you see these sort of scary abbreviations, you can actually dissect them into what you need to know, into things that you know. Now, this morning, I assume that you have seen this sort of thing, right? You have a message on the left, and it's encrypted with some key, and you get an encrypted text. And then with the same key, you're going to be able to decrypt it. And that is then what we should have called maybe same key cryptography, but we call it symmetric cryptography. And that brings me already immediately to the first problem that we will have today, which is that a bit later, people considered, what if we try to use one device to encrypt it and then use another one to decrypt it? And they, for some reason, well, the decryption, that would be a key, that makes sense. But this thing to encrypt it, they also called it a key, a public key, which makes it feel like a bit secret or so, or it's a bit of a weird thing, and it's not really, it doesn't really act like a key at all. It's more like a lock. So what they should have called it was lock and key cryptography or something, but they called it asymmetric cryptography or public key cryptography, and that's what we'll be talking about today. So if you take a global overview, a very quick overview, cryptography is mostly symmetric and public key cryptography. And then symmetric crypto, you saw this morning, we already assume that we have some kind of key, and then we can do all of this amazing stuff like encrypt data or authenticate data and so on. But it assumes that you have a key, and that's not necessarily, in many cases, not the case. I imagine that if you look to the person to the left of you, you are not accidentally sharing a cryptographic key at the moment, right? And the way to achieve that is with public key crypto. And we'll go over 3 domains in there. One is public key encryption, which is the slide you saw before. Encrypting with one thing and decrypting with your secret key. One is digital signatures, and the last one is key agreement. So public key encryption is I want to send you an encrypted message, but we're not sharing a key. And in the end, you'll actually conclude that this should almost never be used, except for this thing we call key encapsulation, which we'll get to in a bit. Digital signatures, actually, those are the things that are heavily used. So you want to send a message and authenticate that you are the one sending this message. And when somebody receiving it knows for sure that you sent it. And this happens in TLS or in WhatsApp or Signal, or even in payments, right? When you tap to pay, that you're authenticating that you are the one making that payment. And by a rough estimate, at least all of your phones are doing like thousands of these digital signatures every day. Key agreement, that's where we come in with this symmetric crypto. It's the scenario where we don't share a key yet, but we do want to share a key. We want to share a symmetric key, but to do so, we will be able to use these public keys. And again, here you use this in TLS or in WhatsApp when you initiate a conversation, for example, with somebody. also used in VPNs. And it's actually super critical to all these applications. We would really be in quite of a dire situation without public key crypto. And also this, your phone is doing at least 100 times a day. Maybe not as much as digital signatures, but still very fundamental for how our digital society even works. And at the moment, you should be like this kid. There is a lot of terminology in this domain, and you probably don't get it yet. And the goal is to change that today. So we're going to do it in 3 steps. First, we need to understand some building blocks on which most of this cryptography is actually based. And these are mathematically, I would say, not too difficult. I hope that I can get you quite far in understanding this, except when we get to this point of elliptic curves, where we'll have to be a bit less technical just to make sure that the subject is digestible. Then we'll take a look at that first category that we saw that I called public key encryption, but we'll specifically look at key encapsulation. And then in the third part, we're going to look at digital signatures. This is also the moment where we're going for the magic trick. So what I want you to do actually is you take a number between 1 and 10, right? And then you will compute 3 to the power of that number. And you don't have to do that by head. You can just use your phone or Wolfram Alpha or something like that. It's going to be quite a big number. But then you'll have to exchange the last 2 digits of that number with the person next to you. And if you haven't met them yet, this is the moment to say hi to them. And in a bit, give them the secret number. The number that you get, these 2 digits, you'll get like 63 or so, you're going again to raise that by your secret number. And then I will count down from 3, and then you'll say both what number you got. So for example, if I would take 7, I would now compute 3 to the power 7. And if you picked 7, you're lucky, because you don't have to do this first step, right? And that would give me 87 as the last 2 digits. Then I would tell my neighbor 87. I get something back, like maybe like 13. And then I compute 13 to the power 7 again. Then in the end, we get 17. So take a few, take like, I don't know, how long do you need? 10, 15 seconds to say hi to your neighbor and to pick a secret number and to compute that, to share that information. Sorry? So you both take a secret number. Yeah.
If you know that number, you will then know what Y is. No, you don't know what X is. You don't know that secret number. That's what you want to tell us, right? It's no.
I went so you exchange your secret your public numbers, these Ys, and now you raise it again, right? So has everybody exchanged secrets and raised again to the power? Because then I'm going to count down from 3, and at that moment, you should both say the end result that you have to each other, okay? So, yeah? 3, 2, 1. So who got the same number for both of you? Huh? So if you got the same number, that's a good first step. Otherwise, you messed up something. Now here's another question: which pair both got 1 as a result? Okay, can you tell me which secrets you took? Okay, so this you should remember that they took 4 and 5, because as homework today, at the end you should understand why this trick works, but also why, for example, they got 1 when they individually chose 4 and 5. Because if you really get the trick here, the rest of the course is going to be a breeze. So what we were doing was modular arithmetic, and essentially when you were in primary school or in high school, you were just used to numbers, and you can add them together and multiply them. And mathematically speaking, you would say that you were living in the world of integers, really. But cryptographers live maybe in a different world. they like to pick a prime number p, so a number with no other divisors than 1 in itself. And then they will work with only the numbers between 0 and that prime. And if you go above that prime by adding two things together, you're just going to subtract that prime number until you're back in this range of 0 and p minus 1. We call this working modulo p. We use this symbol, which looks like an equality, but it's like special equality. When we say that two things reduce to the same thing modulo p, and that world is called the integers modulo p. So very easy example, takes 13. When you subtract 11 from 7, you get -4, but we add 13 back in again to get 9. If you do 3 times 5, it becomes 15, but we subtract 13 so that we're back between 0 and 13 to get 2. And then you can also do like these big exponentiations. And it's a bit tricky to go from there to there. Well, if you're doing mental arithmetic, but for a computer, it's quite easy to reduce things, modulo p. And that's all we really need, and that's also close to explaining the magic trick already. Because the magic trick that we did was sort of this work from Diffie and Hellman. And this is where public key cryptography started. And if you ever need an example of how to write the paper, this is the paper to read, because it starts with, we stand today on the brink of a revolution in cryptography. And that really shows you that these guys were convinced about the paper that they were writing, right? If you read this paper, they really realized that at this moment, the digital world was going to completely change from this work. The funny thing is, they write this in 76, sorry, I mixed this up a lot. And somebody in the Secret Services from the UK actually wrote it down 3 years before, but had to keep it locked in a drawer because they weren't allowed to publish it. So what did they come up with? As before, we take a large prime p, and we're now going to work in this world modulo p. Now, you can call something a generator, modulo p, if any other number between 0 and p minus 1 can be written as some power of that generator. And you can always find these generators for a given prime p. Now, Alice and Bob want to share a key. They each take a secret between 1 and p minus 1, and they compute that exponentiation, modulo p, that we had before. And now that A and B, the capital A and B, these they can share with everybody, and particularly they will share it with each other. Then they do the same step, but with these numbers reversed, right? So Alice takes B and computes B to the power small a, and Bob computes A to power small b. And this K and K prime, exactly what you said by just the simple mathematics of exponentiation, so G to the power A to the power B is going to be the same as G to the power B to the power A, that still holds modular primes as well. And by that principle, they recover the same shared secret. And now what they can do is use that shared secret K to do symmetric encryption, right? But the cool thing here, that was really the revolutionary part, is that all of their communication can be done over a public channel. Anybody can listen in on this and still not be able to derive that shared secret. So that's the shared secret. These are the public keys. And I'm really sorry about this terminology. I really dislike this terminology, but we're stuck with it for, I think, the rest of cryptography. So in the real world, your prime is going to be huge. It's going to be like 4,000 bits. But your generator can be something like 2. For this prime, 2 is a generator. And now what I meant by this public channel is that, okay, if Alice and Bob both do that computation, they're going to share this information. But from this information, I can assure you that nobody in this room is going to be able to guess what their secret A and B were, just because it's computationally completely infeasible. Now you might wonder then, okay, how do we reduce that? How do we make that into concrete problems that we can study and to see how secure this system is? So the first problem would be, I'm given this prime, I'm given this generator, and for A, I know that there's some power, right? There has to be some small a. And the question would just be, can I learn anything about that small a? That's the discrete logarithm problem. The second problem that you could wonder about is, okay, but in real life, I don't just see P, G, and A, but I actually also see B. And maybe I don't actually need to recover small a. Maybe I just need to learn the shared secret, and then I can also listen in on all of their secret communications. So that's problem 2, which what we call computational Diffie-Hellman. Can you learn anything about that shared secret? And we always call the bad person in this Eve, because she's an eavesdropper. Can I learn anything about that shared secret given just P, G, A, and B? Now, it's not very difficult to figure out that if you can solve problem 1, then you can learn small a and small b. And so you can also solve problem 2 at that moment. And then here's another very unfortunate clash for me. We call that a reduction from problem 2 to problem 1. And this always confuses me, in which way you have to point this arrow. But the logic here would be that if you can solve problem 1, then you can solve problem 2. Somehow this arrow always feels the wrong way for me. But that's how we decided to write this down. That's actually the basics of Diffie-Hellman key exchange. That's all there is to it. Now, I told you that there were these 2 worlds, but then actually, for real cryptographers, there is a 3rd world, which is elliptic curves. And now we're going to switch to elliptic curves, because actually working in these huge fields is surprisingly slow and inefficient and not very nice. And then by switching to this world of elliptic curves is going to be much nicer. So we're again taking some prime p, we're again working modulo p, but then we look at this mathematical object that we call an elliptic curve. And we'll get into that in a bit more detail in a slide. But there will be points that satisfy this equation. But the key insight here is that these points, even though we just write down a curve, these points we can add together in a way that makes sense. We can really do arithmetic on this world of elliptic curves. And that should actually be very surprising to you, because if you would write down a general curve, there's no way that you could do proper arithmetic on it that would make sense. So how does that work? So you take this equation, y squared is x cubed plus ax plus b, for example, and you're working modulo p. So a might be something like 7 and b is something like 5. And then you just check which x and y values will fit. You don't get this picture. This picture is if you would do that for like real numbers, like 3.7 or 12.1. But it's much better to work with this picture for you to get any sense of how this is going to work. Because the addition of the points is very geometric. If I have 2 points, P and Q, I will draw a line between them, and that will hit this elliptic curve a 3rd time. And now I mirror that to define this addition. At this point, you should have a lot of questions about why this works, or how this works, or why that even makes sense. Because this is really quite magical that should make sense, that R is really a good way to define addition of 2 points. But for that, you would have to take a different, like a complete course maybe in elliptic curves for that to make sense. So we will just assume that it makes sense, that we can add points together. Because then what we can do is also add points to itself. So we will write that as n times p. If we start with a point p, we'll add p to p. Now we're actually in a bit of a problematic situation, because here we could draw a line through p and q, but we cannot. How do we draw a line that hits p twice? You actually have to take the tangent line. This is the tangent line. And then we flip again to get 2 times p. Now it's easy mode again, because from p and 2 times p, if we add them together, we get 3 times p and 4 times p, and we can keep on going in that way. There's one more sort of thing that I'll have to explain in a bit more of a hand-wavy thing, which is there's also a point at infinity. And this will be 0 in some sense. What does that mean? That means if I take p, and the point at infinity is going to be infinitely far up, so I can draw a vertical line when I want to add these together. That is also a sort of well-defined operation over here. And as you can see, if you really draw a vertical line, you're going to intersect the elliptic curve here again. And then when you flip again, you end up back at p. So it really is p plus 0 is p. And why do we need this 0? Well, because if you're doing proper arithmetic from a mathematical sense, and you know group theory, you know that you will need an identity element, and this is the identity element. So then we can already do elliptic curve Diffie-Hellman, We will take some elliptic curve. We are working modulo p. We take a generator again, and this again will make sense over here. We can look at the points on these elliptic curves, and we can look at all of the multiples of p. I see here that I wrote, of large prime order. And what is the order going to be? It's going to be how often you need to add a point to itself to end up at infinity at some point. We'll call that Q. And then we do the same thing again as we did before. Alice takes a secret value A, Bob takes a secret value B. Alice computes A times P and gets capital A. Bob computes B times P and gets capital B. And then they share A and B. And by essentially the magic of elliptic curve arithmetic, again, if you exchange these keys and you apply your secret to Bob's public key and vice versa, you end up at the same points because A times B times P is going to be the same as B times A times P. And so again, Alice and Bob share a secret key by communicating over a public channel. Now, look that I said at the start here, I skipped over one important step, which is that I said take an elliptic curve E and work modulo P. These are not things that you come up with on the spot when you're going to do elliptic curve Diffie-Hellman. You actually need to be very careful which elliptic curve you're going to take, which prime you're going to take, and which generator you're going to take. And this was a very big topic of research, actually, to pick a good elliptic curve for cryptography. After about 40 years now of elliptic curve cryptography, there are three that are most widely used that I'll go over here quickly. The first one is called curve 25519. And if you know that, then you already know the prime that we'll be working over, because it's going to be 2 to the power 255 minus 19. And the curve will have this shape. Y squared is x cubed plus ax squared plus x, with a being this 486662 value. This was introduced by Daniel Bernstein in 2005 and is now really widely used in a lot of applications. I'd imagine if you go to 2 or 3 news sites in a bit and you would look at what cryptography they're using, one of them is going to use curve 25519 for your communication. It gives you a security of 128 bits and a public key size of 256 bits. And if you compare that to what we had in Diffie-Hellman before, when we were using these finite fields, to get this same level of security, we would be using fields of about 4,000 bits, which is much, much, much larger, of course. And this is also going to be much faster. This last bit you can actually ignore if you don't, if this is your first time seeing elliptic curves. But in practice, you're not going to use actually this equation, but a slightly different one for efficiency purposes. And now you might wonder what is so good about this curve. And really the essential thing about this curve is this prime that it's using, which means that if you want to add things together modulo p, it's going to be much easier on a computer to implement that for this kind of prime than for, let's say, a random prime of big sizes. And that's because it's very close to a power of 2. But we'll not get into computer hardware in this part. The second curve is this curve called P256 from it's also another standardized curve by NIST. But now here this is a bit more problematic, I think. So the prime is okay. It's still a lot of powers of 2. It's still going to be quite efficient. It has 2 coefficients, A and B. A is very close to this prime, but B is this massive random value, essentially. This was introduced by NIST before 2005, as you can see. This was standardized very early. It's also very broadly used. In terms of security and public key size, it's essentially the same. But some people are a bit worried about this thing, that it might be backdoored. And that reason is really, if you ask people why they have this big random number here, it's because they hashed some random data and then came up with this thing. And that's a bit of an uncomfortable explanation. And the main problem here is that NIST, the NSA really has backdoored crypto before. And so people are a bit uncomfortable with the fact that they came up with these random coefficients over here as well. In practice, if you look at the evidence, it's very difficult to say or not, and it's very widely used, and it's unlikely that it's backdoored. They would have to have some kind of massive research advantage over the rest of the community. But still, I can see why people are a bit skeptic. If you're a bit paranoid, skip this curve. The last one is actually interesting. This has a beautiful name called SecP256K1. This one is a bit more natural again, right? So we have a prime that's a bit wonky, but it makes sense because it's a lot of powers of 2. So arithmetic is going to be fast, and the coefficient is just going to be 7. Also introduced in the same set in 2000, but not very widely used until Satoshi decided that this was the curve that he needed in the Bitcoin protocol. And nowadays in cryptocurrencies, you see that this curve is used a ton, like everywhere essentially. It has the same sort of characteristics as the other two, right? 128 bits and 256 for public key size. But there's a clever mathematical trick hidden in this construction over here that is too technical to get into, which also makes it quite fast. Now you might wonder then, why didn't Satoshi just pick this curve over here? I think that would have made sense, but probably what happened is that Satoshi was doing this in like 2008 or 2009 or so, and this one's really only introduced in 2005, so that gap is very tight. So this would have been a risky choice at that point, whereas this curve was much older by then. So I think that's mainly the reason that we ended up with this curve, and also that this is now so widely used in cryptocurrencies, just a sort of quirk of time. That concludes the Diffie-Hellman key exchange part. There's one question that you should still have now, if you've never seen public key crypto before, which is, how do you actually get each other's public key? Because we assume at the start somehow that we have these public keys from somebody else, but how do you know that somebody else's public key is actually theirs? Keep that question in mind, because we're not going to answer it now. For now, we're assuming that we understand these building blocks. We understand modular arithmetic and Diffie-Hellman. And we're now going to look at that second step of public key encryption. And in particular, we're going to look at key encapsulation. So public key encryption is exactly that example that I gave you at the start, right? With these texts. You are, so let's say on the left, you want to send a message to somebody else. You have their public key, and then you can use their public key to encrypt this message. But only they have that secret key, and so only they can decrypt that message. Now, what we would like to do in cryptography is to formalize that a bit. So we'll formalize this into 3 algorithms. The first one is what we call keygen. Keygen, you just say the security level that you want. I want 128 bits of security. And it gives you a secret key and a public key that match your secret key and your public key. And the public key you can give to everybody that you want. The secret key, please keep it to yourself. Now then there's a second algorithm called encrypt, and that's what everybody else will use. They will have your public key, they have some message that they want to send you, and when you throw both of them in this encrypt algorithm, you get an encrypted ciphertext C, this guy. And then you, again, with your secret key and this ciphertext, can use this last algorithm called decrypt, and that will return to you your original message. To get to these 3 algorithms, or to get to a nice description of this, we need a bit more modular arithmetic. So I mentioned this before, the thing about the order. What was the order? Well, it was in the elliptic curve case, it was the smallest number so that you would end up at infinity. But when you're just doing modular arithmetic, it's essentially the smallest power that you can take to get 1. For example, if in the magic trick you chose 5 and your partner chose 4, and somehow you ended up with 1, that was because the order of these things together was 20. But if you look at, for example, the order of 5 modulo 9, it's going to be 6, because if you do this exponentiation, you'll see that you get 1 modulo 9, and that's the smallest integer that will do that. And for 2 modulo 37, it's 36. And actually, that's maybe not a coincidence, right? This 36 is very close to this 37. You might wonder, is that a sort of a common thing? Well, it turns out, you can check what the possible orders are when you're working modulo n with a thing that's called the Euler-Tauschen function. So what we have as a theorem is that the order will always divide this magical function. And for a prime p, that's actually p minus 1. So for modulo 37, every possible order will divide 36. And for 2, it happens to be that it's actually 36. But for a product of primes, like 9 or so, It's actually, so for two different primes, P and Q, the formula is actually going to be P minus 1, Q minus 1. This is actually most that we need to introduce RSA. RSA is the second scheme that we're going to be looking at. It's by Rivest, Shamir, and Adelman, which is where the RSA comes from. A bit more of a modest paper, if you look at it. They just say, this has obvious applications, instead of, we are going to change the world. Even though, if you look at what happened afterwards, RSA became hugely popular in the 90s, 2000s, and still is very much used today. No, I'm forgetting to mention another fun fact about RSA. Also RSA, this was published in 76 or so, 78, was previously discovered by somebody in the Secret Services, was not allowed to publish it, had to put it in a drawer, until they came up and said, we came up with this. Only in 1997 did both of these secret schemes actually get released to the public, saying, actually, we knew all of this already. So how does RSA work? You now take two large primes, P and Q, and you keep these a secret. Now you multiply them together to get n, and that is public information. That one you can share with everybody. And now we will work modulo this phi of n, this P minus 1, Q minus 1. You have to take as a secret number, secret integer e. Sorry, this is maybe the e is not secret. Just take any e. Go prime to that P minus 1, Q minus 1 thing. So they don't share any divisors. The greatest common divisor of these two numbers is 1. Then you take a d, such that d times e is equivalent to 1 modulo phi n, which you can do. There is an algorithm to compute this thing, and you just throw e in there and phi n, and it will give you d. Now this e and n is going to be your public key, and this secret key is going to be d. And surprisingly, to me, in preparing these slides, I actually realized that I've had this lecture quite a few times, and I've never realized this, that the E is because it's encrypting, and the D is because it's decrypting. So that's nice to remember. I never realized that before. So what are we going to do to encrypt? Let's say we have a message. We turn it in some way into a number. We represent it by a number, and we will have to assume that it's smaller than n. And then to encrypt it, we just raise that number to the power e. This gives you a ciphertext modulo n. That's it. To decrypt, you raise the ciphertext to the power d to decrypt. And because we've now in total raised to the power d times e modulo n, what is actually happening in this exponents is that we're not working modulo n, but we're working modulo phi n, because that was essentially always the order of m, right? The order of m is going to, because we're working modulo phi n, d times e is going to be equivalent to 1. And so m to the power de is going to be the same as m to the power of 1. So it gives you back m. That's what I was going to say. Again, if you look at a toy example very quickly, you have to remember that we are now picking the primes each time, right? In the previous case, in elliptic curve Diffie-Hellman, we picked a prime and then the rest of the world was working with it. But now actually these primes are going to be yours to keep secret. 19 and 23, that would give you 437. And then this phi n is just going to be 18 times 22, which is going to be 396. Let's say you take a randomly e being 13. Then you can apply this algorithm to find d. Modulo this 396. If you are a first-year student, you will always pick modulo n for some reason. But make sure to do it modulo this phi n. That will give you d is 61. And so your public key is really just that e, 13. P times q is 437. And your secret key is 61. And then the encryption is just raising to the power and using modular arithmetic. Again, you're going to be wondering now, okay, what is like fundamentally the hardness here, right? What can we reduce this problem to? And the first one is quite easy. Namely, if you're given n and you would be able to find p and q, then you can actually do this, find this decryption step as well. So this first problem is actually just integer factorization. Given a very large number, that's the product of two primes, can I find the original primes? Surprisingly, you would think maybe people studied this in the 1950s or 60s, but surprisingly, people already looked at this kind of problem in like 1890, even before they had actually any kind of use for it. The second problem that you can just get is more cryptographically intuitive. Let's say you're given the public information, right, N and E, and you're given the ciphertext. What can you learn about the message? That's more of the RSA problem. Now, clearly, again, if you can solve this problem, you can solve this problem, but the other way around, we don't think that's true. Well, maybe some people think it's true. It's not known if that's true or not. We mostly base our hardness based on this integer factorization. This is what we think of. If we know how difficult integer factorization is, we know how to make this scheme secure. So how difficult is integer factorization? Well, luckily, they released also with RSA, or the RSA Foundation, a lot of challenges. So what they just did is they took primes P and Q that were suitable, multiplied them together to give us challenge numbers of a certain bit size. And you can see that they started with that in the 1990s, where people were able to factor these challenges of like 270 bits or so. And since then, since about 2020, that has quite steadily increased, as you can see, by just mathematical improvements in integer factorization. And the record stands at 829 bits in February 2020. It's also a bit surprising that there has been improvements in integer factorization, but somehow not in these RSA challenges. So what you find mostly nowadays is actually that people are using RSA 2048, where 2048 is the number of bits of n. Is that secure? Well, it would be surprising if that's not secure for the next few years, but these big organizations like NIST and so on recommend to change away from RSA 2048 before 2030. And if you would need to keep secrets for a longer time, they used to recommend 4,000 bits. But actually, at the end of the story, we'll get back to the long-term security of RSA. But anyway, this is why you will often see this number, RSA 2048. That's where it's coming from. Now, actually, I've been a bit vague about what secure actually means. Of course, it somehow means that you can break a scheme in some sense. But what does that actually mean, for example, for RSA? And we're going to formalize that a bit more now. What we usually do is we have challenges, essentially. You're playing a game with someone. So for example, let's say you have two messages. And I will encrypt one of them with my secret key. But I'm not going to tell you which one. And then the challenge for you would be, can you guess if it was M0 or M1? Well, you can just guess one of the two, but then if we play 1,000 times, you're going to get it roughly right 500 times. So can you do anything better than just guessing 50-50? And if you can do anything better than guessing 50-50, we say that you win this game, and then the scheme is not secure. This is called what we call indistinguishability. Now, we actually have different powers that we can give to an attacker. We can assume that they just, as we had now, are given sort of the public information that is available, right? And that includes that we assume that an adversary can also encrypt any message. Because it's a public system anyway, we can assume that you can always... I should have put actually a public key here. That's my mistake. We can assume that you can encrypt any message because it's a public key encryption system in the first place. That attacker model is what we call a chosen plain text attacker. So that's why we call it CPA secure, because they can choose a plain text to encrypt. And we call that combination of achieving indistinguishability when the attacker can do chosen plain text, IND CPA. From this definition already, if you just saw RSA, you're going to be a bit confused, because clearly that's not true for RSA. For RSA, you can just encrypt these yourself and just check which one matches the ciphertext. We'll get back to that in a bit. You should have that confusion. We actually want to assume much stronger attackers as well, because we want our cryptography to be as secure as possible. So we're going to essentially, in a different model, we're also going to give an adversary access to what we call a decryptor. Here, we can actually give it any ciphertext, and it will decrypt that for us under the secret key. Here I actually mixed them up again, so this should be the secret key again. And you can do that for as many times as you want, for as many ciphertexts as you want, until you get your challenge. Then you get your challenge, M0, M1, C prime, and now the guess is, can you do better than 50-50 or not? If you're still secure in this model, here we call that chosen ciphertext attackers because they can choose ciphertext. We call that CCA1 security. And the 1 implies a 2, which is this one. In this case, now you have full power, essentially. You're allowed to decrypt anything before you get your challenge. And after your challenge as well, you can still decrypt anything you want, except the challenge that you were given, because that would make it very boring. And now you have access to essentially anything that you want, except for something literally decrypting the ciphertext. Is your scheme still secure? And that's the holy grail for cryptography. That's really what we want to have for our schemes. It's CCA2 security. The problem is, already for RSA, we're not even this chosen plain text secure, right? Because RSA is deterministic. If I give you the same message, it's going to be encrypted in the same way in this textbook version that I gave you. So it doesn't really achieve that much security in the first place. And that's what causing a lot of problems in RSA. But then there's also many practical issues for RSA where you need to pick these primes in the right way to not have any weakness, and you're going to have some trouble with implementing these sort of things. And there's this problem with randomness. So we're going to have to add randomness in some way to get a secure version of RSA. And the third problem is really that it's going to be incredibly slow if you're going to encrypt more than, I don't know, if you're trying to encrypt a book with RSA, you're not going to have a fun time. Let's see how these issues are addressed in practice, right? So the randomness, we can add that by ourselves. What we're going to do is something called padding. Actually, I should mention first, it's going to be impossibly slow for larger messages, so we're not going to use public key encryption for large messages. We're just going to encrypt a key for symmetric crypto, and then we'll use symmetric crypto. So let's assume that for now. So what we can do is when we're encrypting this key is just to add randomness before we encrypt it. So we pad our message with some randomness so that our key is, so that together they will have the same size as what we had, this modulus, this 2048. And that will prevent also this deterministic problem that we had before, this CPA security problem. Easiest way to do that would be you have a key of k bits, usually 128 or so. You have a modulus of 128, so 2048 bits. So there's a lot of spare room here. We put the key in the back, we add a 0 here and a 0 here, and then just some random stuff in between. Now we have a lot of randomness, so if you call the encryptor on message 0 and message 1, it's not going to give you back the original ciphertext. But for decrypting, it's not a problem, of course, because when you decrypt it and you see this structure, you just ignore this part and you get the key that you wanted. They call this PKCS number 1 v1.5, which is again a very pleasant way to describe a scheme. And you somehow would not imagine it, but this was actually broken as well by this guy called Beichenbacher, who came up with a very clever attack when you just do this normal padding that you would assume is the most sensible thing to do. It's the first thing you might come up with. Here, the problem is if you do this for RSA, and you get your ciphertext, and now you feed it to this sort of decryptor, it's either going to look like this, right? And then it says that's good. Or if you messed with the ciphertext and it doesn't look like this, it's going to give you an error of some kind. But there you can do a clever trick. Namely, if you take your ciphertext and you multiply it in the right way, you can check if if you still keep this structure of the 0 and 2 over here, you actually learn some structure about another part of what you were encrypting in the first place. The whole paper is very nice to read. It's a bit more technical than this, but the essential idea is that you have something which tells you if your ciphertext is the encryption of something in that form. If you have an oracle like that, you can probe that continuously to reveal actually the secret information that you were trying to hide. And the solution then is even more complicated padding. So the current state of the art maybe, or the standard one is called OAEP. I'm not going to go in full detail about what this padding is. It looks like this, and it's a bit gnarly because you're going to add these sort of random bits over here, and then you need things that are called masking functions. And I don't think you would have seen these this morning in the symmetric key intro, symmetric crypto intro. They essentially sort of hash to a sort of random value, and you combine them in the right way, and then you get a right way to pad your keys for RSA. But as you can see now, we just essentially took a bad scheme to start out with, and then we're trying to patch and patch and patch it until we get a functional scheme, which is a bit annoying. That's essentially what happened for RSA. This will mask this internal structure for Bleichenbach, so that is no longer an attack. But now our scheme is just more complicated than we would have hoped for, and implementing it in the right way and so on. If you're doing this by yourself, you're going to make mistakes. So essentially, the idea is that this whole public key encryption is just using RSA is not very pleasant. So let's just go back one step again to see what we're actually trying to achieve. What we tried to achieve is that we could share this symmetric key in the first place, because we only want to share a key, and then we'll do symmetric crypto anyway. So instead, we can sort of encapsulate a key using a public key and then a secret key to rederive it, and use that one for symmetric crypto. But that's actually maybe a different set of algorithms than what we need from public key encryption. We can do this with public key encryption, but maybe we can make something slightly lighter that is going to be more suitable for our purposes. This is a key encapsulation mechanism. It's 3 algorithms, and the first one is very similar to what we had before. You get a secret key and a public key. But now for encapsulation, you only need to take the public key, and it's going to give you a shared secret key and essentially an encryption of that key. Now I called it encryption because you will have RSA in your mind, but in fact you can just call this encapsulation as well. It doesn't have to be an encryption function in that way. And now for the decapsulation, so going from that ciphertext essentially back to your shared key, you need another algorithm that takes your secret key and the ciphertext and returns this shared key. And it's fairly easy to see how we would be able to do this now with RSA, right? So we will call that RSA chem. And the setup at the start is really the same. We take again 2 primes, which we keep secret, multiply them together, work modulo this order thing. It's all the same setup. So your public key is still E and N, your secret key is D. But now instead of encrypting messages, for encapsulation, we generate a random number that is smaller than N. We encrypt that, we raise that to the power E, and we also derive a key from it. I don't think this was discussed this morning during symmetric crypto, but in symmetric crypto we have functions where essentially you would feed this random number and it sort of derives a key from you for you in a deterministic way. And now that's your K and C. And then to decapsulate, well, if you're given C and you have the secret key D, you're going to be able to recompute R. And you can also apply that same KDF function to get K. Now we've solved quite a few problems, actually. Let's first talk about the security of this thing. This has now changed a bit, right? So we defined a new sort of scheme, RSA chem. And so we also need to adjust our notion of security here. So the challenge is no longer this indistinguishability thing, because we're not going to encrypt messages. So the challenge instead is I will generate a valid pair, K and C, and I will generate some random key, K prime. Now either you're going to get the right pair or the one I messed up. And now your question is, can you actually figure out which one is which if you don't have the secret key? It looks a lot like this indistinguishability, but it's sort of formed for camps now. Again, you can decapsulate as much as you want. We're going to take this strongest attacker model, except of course decapsulating our C over here. And that's essentially what we would hope for this IND CCA2 security again. So that's sort of the equivalent for CAMs. Now for RSA CAM, we got rid of the problem of padding. I wrote here as a thumbs up, cannot be used for encryption, which is really a good thing now. Why? Because, so this is a true story. I was once, when I was working in consultancy, I was trying to explain RSA to some clients, and they came back very happy a week later that they were able to encrypt very large messages with RSA, which was of course not what we were hoping for. We were trying to get them to do this sort of key encryption. But here you cannot mess it up, really. Here you can only do key encapsulation. And the implementation will also be quite a bit simpler. So in practice, this key encapsulation mechanism it's much nicer than just general public key encryption. And because the only thing that we're really trying to do with this is to share keys anyway, that's going to be suitable for what we need. I wrote down some other chems here so that you might be familiar with any of these, but you will use different mathematical principles, but the essential objective is going to be the same. Now, we have now two ways to exchange a key. We can use a chem, or we had this Diffie-Hellman thing. So what is really the difference here? For Diffie-Hellman, let's assume that we both have each other's public key. If you apply your public key and your secret key, you both actually can already derive the shared secret, right? You don't even have to interact if you assume that you have each other's public key. So even without interaction, you would be able to immediately send already, I don't know, symmetrically encrypted data or so. So it's non-interactive key exchange, and we call that a NIC. Whereas for a chem, you always sort of assume that one person is initiating this communication, right? Even if you have each other's public key, what you do when you initiate it is that you encapsulate something random with that public key. So it requires this initial interaction. And now in cryptography, for some protocols this really doesn't matter. Chem is fine. For other protocols, you really need this non-interactiveness of the NIC. So it cannot work with like RSA chem. You would really need to use Diffie-Hellman. Keep that in mind because it will be important a bit later. So what is our conclusion? We discussed this part, and we discussed this part, and we actually saw that this is actually also just related to sharing this key for symmetric crypto. So we have resolved a few of these things, this RSA and EC and Diffie-Hellman. The big thing that we still need to talk about is, of course, here these digital signatures. That's going to be the last part of this talk. So what are digital signatures? Well, actually now we've seen two primitives already, and it's been the same setup every time, right? I tell you first intuitively what the idea is. Then I give you this formal definition in terms of algorithms. Then we define security properties, and then we define an attacker model. And that all together, it sort of discusses this abstract idea of a primitive, but that's really distinct from this instantiation of it, right? So RSA chem is an instantiation of a chem. Diffie-Hellman key exchange is an instantiation of a NIC. So these are actually cryptographic schemes, so RSA, Diffie-Hellman. And for these things, that's on which you do your cryptanalysis, right, of your hardness. Here's where the hardness problems of RSA and Diffie-Hellman came in, or of your scheme itself, of the protocol. And then we also have this area for physical security. So if you're actually running this on a computer, what can that physical device, the information from that, what can you learn from that? You take all of that into account in your sort of general cryptography process for your general security of the thing. But this is a bit more structured than what I've been doing so far. So also for digital signatures, we're first going to look at the intuitive idea and then the formal definition and so on. So the intuitive idea is very simple. I have a message. I sign this message with my secret key. And if you have this message and the signature and you have my public key, you can verify that it really was me who set this signature. So you get a verification algorithm that tells you, yeah, this was really a signature set by Krijn. In the algorithms, in the formal definitions, we again get three algorithms. The first one is this key gen algorithm, and this is really almost always the same for these kind of things, right? You want some level of security, and it gives you a matching secret key and public key. For signing, you take that secret key in a message, and it should return a signature. And then verification, you should take a valid signature and the public key, and then return true. Or if somebody tampered with this signature, it should return false or invalid. And this should achieve a few things. First, what it should achieve is authenticity. if you get a message with a signature from somebody's public key, it was really them that sent this message, or at least set this signature on the message. It also achieves integrity, so that you didn't tamper with this message, right? The message is really as it was meant to be. And the last one is a bit more tricky. It's non-repudiation. In some sense, if you have those two things, so now Tintin can also never deny that he actually signed that message, because he's the one that put it in this signing algorithm. He's the only one with the secret key. If you get that message with that public key, it should really implicate him like he signed this message. What is going to be the security for us? It's going to be unforgeability. And this is also very intuitively, very much makes a lot of sense. It means if you don't have the secret key, you should not be able to make a valid signature, right? Because that would, then we would lose all of the things we just had. What does that mean? There's actually 3 levels of strengths that you can assume here. The first one is a total break. And a total break would be for any message that you want, you would be able to sign it, get a valid signature, even if you don't have the secret key. And then your scheme is completely worthless, of course, if people can do this. But we also want to assume already a much milder condition. For example, a selective forgery. In this case, you choose a message, and then you play this challenge of trying to forge a signature for this message. But that's not even the weakest variant. The weakest variant is existential forgery. This is where you start your challenge, and we'll see what your powers are in a bit. And at the end, you're going to provide a forgery of a message that wasn't signed before. But it can just be a message you previously had and a signature you previously had, and that you sort of tweaked a bit. If they can still pass a valid signature, pass as a valid signature, that would be already an existential forgery. So what is the attacker model here? We assume that an attacker can request, like with this decryptor that we had before, but now a signing machine. So they can request a signature on any message that they want. And then we want the combination of these two things. So we want unforgeability, actually this existential variant of it. In this model, the CMA model, we will call that existential unforgeability under chosen message attack. So just to quickly recap, you can sign any message that you want, and now the question is, can you find a new message that you can now find a valid signature for? That is going to be what we hope to achieve for digital signatures. Now let's look at RSA signatures as an example of a public key signature scheme. The setup for key generation is going to be exactly the same, right? We are given 2 large primes P and Q, we keep them secret, etc. Public key is still E and N, the secret key is still D. Now the signing part, this is actually the reverse of what we did before. Given a message, we again hash it to some number smaller than N. And the signature we just raise to our secret power D, which was what the decryption was before, but now it's going to be the encryption. And now anybody with the public key can verify that if you raise this sigma to the power E, you should get again back H if it was a valid signature. You shouldn't assume that this is always, it's not like, this is not a general thing. If you have an encryption scheme, you cannot just flip around decryption and encryption and hope to get valid signatures. This is for RSA, this is the case that these things are very similar, which is kind of nice on an intuitive sense, but in general, digital signature algorithms or key encapsulation mechanisms are very, very different constructions. Now, again, this is going to be a deterministic thing, and it's still not this EUF CMA secure. But you can fix it again by applying the right padding and so on to make sure that you get a secure scheme. But maybe the conclusion by now is that actually, if you want to do this properly, there's something called RSA PSS, but it feels like we should have stopped using RSA already years ago. And I hope that I can get this across a bit, that really RSA was not the nicest scheme to work with in the first place, in my opinion. And the elliptic curve Diffie-Hellman stuff and so on was already quite better. And you actually see that as well in sort of the adoption of which scheme is used nowadays. It's going to be much more of this Diffie-Hellman, elliptic curve Diffie-Hellman than RSA signatures. So, sorry. This one and this one. So here, yeah, okay. So here, this can really be any message that you want. Here you choose a message. Now you can request signatures on any other messages, right? You can request as many as you want, and then you're wondering, can I now also forge a signature for this specific message? Yeah, I'm sorry. I'm having a bit of a difficult time to explain it here on the spot, but yeah, let's look at it a bit later. Yeah, same for me. Sorry about that. Where was yeah? So I was going to say, can we also do signatures using this sort of Diffie-Hellman modulo P arithmetic? As a reminder, what we were doing, right? We took a prime P, we were working modulo P. We assume that this discrete logarithm is difficult, given G and GA find A. And now we're trying to find a way to make digital signatures from this, right? These three algorithms that we had, especially the signing and verification algorithm, can we do that in a way so that the difficulty is based on this problem instead of this integer factorization problem? We need a bit more material here because it's a bit tricky. So we had elements and we know what the order of an element was, but now we want an element of G, so that modulo P, the order is a large prime. So Q is new prime, which is the order of G. So we have to pick P in such a way that Q divides P minus 1, because we know that the order of any element will divide P minus 1. And so if we want that to be a large prime, we need to make sure that we already have that when we pick P. Now, how do we do that? You can take a random h and compute this element, h to the power of P minus 1 over Q, modulo P. And this gives you an element G, and this element G is either going to be 1, but very often it's not. If it's something else, it's going to be an element of order Q. Because if you raise G to the power Q minus 1, in total you have raised to the power P minus 1, and any order divides P minus 1, so it's always going to be 1. So the resulting element G now has order Q. And now we're only going to work with these powers of G. So it's not all of this Z modulo P, it's just going to be the powers of G in this case. In some sense, actually, we were doing the same before, but I didn't explicitly mention it. We will call that G. Why do we need that? You will see that in a bit, because this is going to be the security parameter, this Q. So we're working modulo P. We have this group G, generated by this small g. We also need to assume a good hash function, but I hope from this morning that you still remember what a hash function is. Now you take a random number between 1 and Q minus 1, and this is going to be your secret, of course, and you compute the exponentiation of G by X, and that's going to be, again, your public key. Okay, so far it's very standard discrete logarithm stuff. Now, if you want to sign a message, first you hash it again to a number smaller than Q. Now, this is very important. You choose a random other number K, and you compute G to the power K modulo P, and then modulo Q. This setup is a bit convoluted, I know. This is a bit of a weird way to start a scheme. We will not really see intuitively why this is going to work. I'm a bit sorry for that. Now, if you compute this value S as a combination of your message, your public key, your secret key, and this value R, and then multiply all of that by the inverse of this K, that will be your signature, this pair R and S. If one of these is 0, you should start over again, but that's sort of small technical details that are not very important to understand what's going on. For verification, you reverse sort of these computations, but with the information that you have. So W is going to be the inverse of this S, which everybody can compute with the public information. You also compute the hash of this message. And then if you verify that R is equal to this, to the sum on the right over here, you can actually work that out. So if you have some time left, you can work out that if I fill in H and W over here, and I rewrite Y as G to the power X to the power RY, you will see that this is just done with public information, but it verifies, it really does verify that the signer could only compute that if they had X, and if this is a valid signature in that sense, right? So that R is really equal to this part. This is what we call DSA signatures, but we're now going to do the same trick that we did before. Namely, we were doing stuff for these finite fields with prime orders, but we're going to move everything to the elliptic curve world. So what was the essential step here? Where we used to have G to the power X modulo P becomes this multiplication of a point. So X times G on an elliptic curve. So the setup is now, again, we are working on an elliptic curve, one of those standards one that we have. And we have a point P there of a very large prime order. And all of those elliptic curves have such a point P, which we call the generator, which is always given in the setup. And we have this hash function again. So in the elliptic curve case, again, your secret key computation, your secret key is just going to be any random number, and your public key is now going to be, you take the starting point P and you multiply by this X. And here, so you get a slightly different hardness problem, right? So this is still something we call the discrete logarithm problem, where you're given Q and P and you're trying to find X. And this is still very difficult on an elliptic curve. And actually the signing and verification is almost the same. There's some small technicalities to make that work. Again, you choose a random K. Again, you do that computation of K times P. Now you set R just to be the X value of that point, right? We get a point on our curve XY. We'll just need the X value here. Again, we compute the same sort of value S that is going to work out for us in verification. Because in verification, now the computation is slightly different because raising to the power here becomes multiplication on the right. But this sort of multiplication over here becomes addition on our elliptic curve. But you will see actually that there is this similarity, right? U1 is going to be H times W. U2 is going to be this R times W. The G is the original point that we have over here, which is just going to be this point P. And the public key is going to be this Y, and as all for us, that's going to be this Q. So if you believe this part, it's translating it to the elliptic curve part is maybe more, if you're looking at elliptic curves as difficult mathematical objects, more difficult, but the protocol itself is really very straightforward, a copy-paste essentially. And you verify it again if your X1 agrees between these two values. How are we on time? We are pretty good on time. This ECDSA is actually, so this is a very scheme that is very, very often used. So this is us now, I hope. We discussed all of the three things that we were going to discuss. So you had public key encryption, which was mostly key encapsulation. And then you have these digital signatures, using them for TLS or tap and signal. And again, this key agreement for this symmetric crypto. So we are quite a bit happier now. We understand a lot of terms. And actually, I was looking up now what are maybe some common cryptographic suites that you might encounter in the wild. They look a bit like this. They always have very scary long titles, but we can dissect this now to understand what is going on with all of the information we have today. So for example, take this TLS protocol. This last bit, let's start here. This bit just means ECDHE, means Diffie-Hellman using elliptic curves. And the key is going to be used only once. It's an ephemeral key. And if you throw those letters together, you get ECDHE. That ECDSA part is what we discussed before. That was the signature part, right? This is the key agreement part. This is the signature part. Again, digital signature algorithm using elliptic curves gives you the ECDSH. And then that last block is then the symmetric crypto that we're going to use, which was hopefully covered either by Tim this morning or it's not going to be part of the public key part. Sorry. So we are getting the signatures here and the shared keys here just to ensure that we can do this symmetric part. Getting back to the original problem, I told you, so we were doing symmetric crypto for the bulk of the work, right? But we required a shared key, and then I told you, okay, we use public key crypto to obtain that shared key, but we still had this problem of how do we actually then know that this is your public key? How do we authenticate all of that? And this is sort of a general delay of problems, right? We took a big problem, made it into a small problem of a shared key. Now we still have this problem of a public key. And now I'm actually going to do the same thing, because I will not explain it. I will delay this problem because it's talking all about PKI and trust infrastructures. And that is a lecture that Bart will give. I think it will be mostly in this part tomorrow at 10 about PKI and identity management. So there you will actually finally get the answer for this whole thing about how does that work? How do we know that we can trust somebody's public key? We have a bit more time. That's good because we have solved all of these things, but now actually there is a massive problem, which is this guy with his quantum computer. If you recognize this guy or the quantum computer, then you might have probably expected that at some point I was going to need to discuss quantum computers, right? Because this is going to cause a lot of problems for public key crypto. And if you believe that we will ever build a large enough quantum computer, and I think we will, then we're going to have a lot of problems with this RSA and Diffie-Hellman stuff. And the reason is as follows. This was the situation we just had. We reduced all of that to these problems, right? If this is difficult and this is difficult, most things should be fine, we think. But that's exactly the thing that these quantum computers break. So there is a quantum algorithm that will solve this problem and this problem. It's by a guy named Peter Shor. It's always very pleasant that if you can discuss him because he has amazing pictures that you can put on slides in a paper in 1995. And also in terms of modesty, if you look at RSA to Diffie-Hellman modesty of papers, giving the first examples of quantum cryptanalysis, I think is a good level of modesty in between the two we had before. Phenomenal paper, a landmark paper, because it really says that this RSA and Diffie-Hellman would be really completely broken if we have a large enough quantum computer. So what that means for this lecture today is everything I told you is what we are using today well, not everything, but what we were using up until at least a few years ago. And all of that would be broken if there is a large enough quantum computer. And to be safe again, we'll actually need to move to newer problems, different problems. Now you might think we need to move to something using a quantum computer. This is not the case. We were essentially extremely unlucky in the fact that we chose these two problems to base all of our public key encryption on, even though there are also other schemes that we had that were just a bit worse, that are still fine. We were just incredibly unlucky with this, that exactly these problems are broken by a quantum computer. So there are still a bunch of problems that you can still run, like cryptographic schemes that you can still run on your normal computer. You don't need any quantum hardware, but we think that these are resistant against quantum computers. They are a bit more mathematically complicated. And the good thing is that you'll get a lecture on that in a bit. But I should have said that a bit later, I think. You'll get a lecture on that, I think, on Wednesday. But this is also why I wanted to highlight this difference between chems and nikes so much. Because in a post-quantum setting, what you will see is that these chems, we understand how to do that quite well. We have now, since a few years, a standardized post-quantum chem called MLChem, and this seems pretty good. And if you look at what your computer will be using for TLS, there will be many instances already where people have switched from this RSA or Diffie-Hellman to this post-quantum MLChem. The situation for digital signatures it's a bit debatable. There are standardized schemes here. One of them is ML-DSA. It's okay. It's not perfect. The signatures are much bigger than what we were used to. there's a lot of improvement that we can do there. And this is also where a lot of research is currently going on in post-quantum crypto. And this Nike thing, the one that was essentially very wonderful for us for the last 20 years, this is really problematic. We don't really have this in a post-quantum setting. They do exist, but they are extremely slow. But as I told you before, there is a significant difference between this non-interactive key exchange one and this interactive CHEM one. There are some protocols, there are a lot of protocols really based on the sort of the non-interactive nature and the group structures that we have here. And we simply do not have that post-quantum. So I hope that that's enough of a teaser for you to be super hyped on Wednesday when we get a session on post-quantum cryptography, which will talk about all of this stuff in much more detail, and also about this migration for the internet. So how do you do TLS if you want to do it in a post-quantum world? That's all that I had. We are right on time. We still have 10 minutes to go, but I think it's good to have maybe a bit more early coffee.